Okay, so now that we've defined some of the stuff for periodic motion, okay, our focus, like I said, is going to be simple harmonic motion. So we want to understand what makes a motion simple harmonic. Okay, so first I'm going to give you some definition or some thing, and we're going to prove this along the way. Okay, so first of all, for the motion to be simple harmonic, okay, the either the position or some angle, something has to behave according to either the sine or the cosine function. Okay, if that's the case, then life is good. We have simple harmonic motion. Now we ask the question physically, what must happen? What are the requirements for something to have simple harmonic behavior? Okay, and the answer to that question is that if an object moves under the influence of a linear restoring force, the motion of the object will be simple harmonic. Okay, so what the statement says essentially is this. We can do this with the keeping the mass spring system. We'll use that as a basic example and then derive a lot of the stuff for that. But basically what it says is this: if F is equal to some negative k times x, okay, where k is any constant, x is x is the position, F is the force, and here you see that F is linearly dependent on x, and the negative sign makes it restoring. Okay, the fact that essentially it wants to bring the thing back to wherever it was, back to equilibrium. Okay, so what it says is if F is equal to negative kx, then x will have this behavior, will be plus, will be some constant times cosine of some function of this sort. Okay, we'll understand all the parts of this equation very quickly. But what it says is if F is equal to negative kx, okay, then x can be either a sine or a cosine function. But instead of writing it as a sine or a cosine function, we write it this way, and I'm going to show you why we can say that. Okay, and I'll show you in a very quick way how any sine or cosine function, okay, or rather the sum, any linear combination of a sine or cosine function could be written as in this term, in this form, either a cosine omega t plus or minus phi. Okay, so this is the behavior. What it says is that any time the force is a linear restoring force, then the position will change according to either the sine or the cosine function. This makes life very easy, because if we look at some physical system, and then when we once we write down the forces for the system, if we notice that the force behaves according to this equation, okay, it is negative of some constant times x, alright, then we know that the behavior is going to be like so. It is going to be either sine or cosine behavior. Okay, in fact what we can do is I'll write another statement and we'll prove this soon. Instead of force, we can write, if we know that F is equal to ma, so I can divide both sides by a and rewrite this as F equals negative k over m times x. And actually we always typically write this as negative omega square x. Okay, so just take this of where omega is square root of k over m, and we're going to show all this in the upcoming videos, but this is just to give you a preview of what is to follow, just to give you an overview actually. So this a is negative k over m x, and we'll write instead k over m as omega square. Then what we know is that, let me put if a is all this, then x is equal to a cosine of omega t plus or minus phi. Okay, it all depends on how we set the problem up. Okay, phi could be positive. Okay, so what you have is this. These are the things that we're going to show. Okay, and like I said, the motion can be defined either by a sine function or a cosine function. So in general, okay, in general, we can write x as either, you know, some constant times cosine of omega t plus another constant times sine of omega t. But what I'm saying is that instead of writing it this way, I could just write it this way. In fact, they're two equivalent things, provided we define things correctly. Okay, so this is, you know, something that we need to understand. So a basic statement here is important. Okay, so if the force is a linear restoring force, okay, which makes the acceleration also linearly dependent on the position, the negative sign is very important here, because if the instead of a negative is a positive sign, then the object just gets kicked out and never comes back. Okay, so we want the object to come back, and when this happens, what we know is that x will be equal to a cosine omega t plus phi. Okay, and I've kept saying that in general the x is a cosine omega t plus b sine omega t. Okay, or some constant, you know, instead of writing it as a and b, let me write this as c and d. Maybe that way you don't confuse the a with this a. So c and d, and what I'm saying is that this thing in red is equivalent to writing it as some other constant a times cosine omega t plus or minus phi. Okay, so we have all these things. Now before we move on, let's also just look at something here. Since we've already written some of these things down, this a cosine omega t plus or minus phi, let us look at you know, very quickly how we can obtain the time period from this thing. Okay, so if I were to graph just the cosine function, okay, if I were to just graph cosine of theta, all right, what we know is that cosine of theta would start somewhere around, you know, at 0 it'll be equal to 1, then it goes down to, at pi by 2 it goes down to 0, so this is 0, at pi it becomes minus 1, at 3 pi by 2 it hits 0 again, and then at 2 pi, okay, it comes back to its original position, and then from here onwards it will keep on repeating itself again and again. Okay, and these are things that you already know from your elementary, you know, trigonometry. So we know that the period, okay, and again this is not time period. Okay, let's understand this. The theta here is always going to be an angle. The theta that the cosine, okay, when you write cosine of theta, okay, the theta which is the argument, okay, this we know is always going to be some kind of an angle. Alright, so when we talk of a period for just the cosine function, okay, without trying to, you know, get time involved in anything, then what we know is that the period is going to be 2 pi. Alright, so which could be, you know, if you want to think of it, it will be the angular period. Okay, so the thing will repeat itself after every 2 pi change in the argument of the cosine function. Okay, now cosine theta, it's easy to graph. Now what happens if instead of cosine of theta you have cosine of 2 theta? Okay, so if you're trying to graph cosine of 2 theta, once again on the same thing, you have pi by 2, you have pi, you have 3 pi by 2, and then you have 2 pi. Okay, now how do you go about graphing this? Like, what is the change? So this is, you know, in order to figure out what the time period is going to be now, all you need to do is think of, you know, instead of thinking of 2 pi, think of it as some kind of box there. Okay, and what you have is you have cosine of, you know, something hidden in the box, and what we understand is that if box, okay, changes by 2 pi, so box goes to box plus 2 pi, okay, then we know that the function is going to repeat itself. Alright, so now, which means that if 2 theta, okay, is added up, or 2, you know, it gets changed to 2 theta plus 2 pi, alright, or if theta changes from theta to theta plus pi, then we know that the function will repeat itself. Okay, so a simple way to remember what the period is for, for cosine of n times theta, just replace n times theta with 2 pi. Okay, and that way you can replace 2 theta, sorry, the theta can be replaced by pi divided by, or 2 pi divided by n, and that gives you the total that gives you the period for the function itself. All right, so let's understand this again. So if what we know is that if box changes by 2 pi, then the function will repeat itself. But what is box? Box in this case happens to be 2 theta. So if 2 theta changes by 2 pi, so if 2 theta is equal to 2 pi, all right, then we know that it will change, and so that gives me theta equals 2 pi divided by 2, which happens to be pi. Okay, we can figure out the time periods this way. So what we know, or rather not the time period, the period for the cosine function. So you start at 0 now instead. Okay, so you'll go back down here, and then you go here, and then you come back all the way up here, and then you keep repeating this, and you see that all you've done is you've compressed the function. So anytime you multiply the 2 times, anytime you multiply anytime the argument is some multiple of theta, all right, instead of just theta, then the time period just changes. So if we had cosine of n times theta, where n can be any number, okay, not just an integer, it could be absolutely any number, then the period, okay, the period for this, okay, could be simply obtained by doing 2 pi divided by n. That's it. Take the entire argument. We want this entire box to change by 2 pi. So in order for the entire box to change by 2 pi, okay, we need the theta itself to change by 2 pi divided by n, because then when I multiply it by n, it changes by 2 pi, and I get back my original period for the cosine function. Okay, all right. So that's one thing that we're going to need. So in our context, what we have is we have cosine of omega t. Okay, let's ignore the phi for just now. We don't care about that. And now here we're going to graph it with respect to t, where t is time. Okay, again, keep in mind that omega times t, okay, the whole product omega times t, okay, is the equivalent of some kind of an angle. Okay, so once again, the argument cannot be time, it has to be an angle, but t itself is time, so omega happens to be 1 over time, which you already know. So here when we graph this, okay, if I'm graphing it with respect to t instead, what we understand is that the function will repeat itself, okay, when t changes by 2 pi divided by omega, and this is how we get the time period for the cosine function. Okay, so what we know is that the time period for if x is equal to a cosine of omega t plus phi, then the time period is 2 pi divided by omega, whatever the value omega will be. Okay, so depending on the situation, omega will take different forms, and then we can use that. Okay, we can just plug this into this equation and we get all that stuff. Alright, once we know the time period, we can also find the frequency, which is 1 over time, which is omega over 2 pi, and everything is good. Okay, alright, so in the next video what we'll do is we'll look at the simple harmonic behavior of a pendulum, not a pendulum, what am I saying, the mass spring system, and then we'll develop all the stuff for it. Alright, we'll see what the time period is and what the speed is and all kinds of stuff. Alright, great.